A limiting reactant is a reactant that is used all in order to form the product. So by knowing how much I started with, I can easily relate it to the product that is formed because I used all of this reactant in order to form the product. It's called a limiting reactant or a limiting reagent because it is one of the reactants. So here in this equation, I am reacting fluorine and I am reacting it with hydrogen. So all the fluorine reacts with some of the hydrogen, not all the hydrogen, because the hydrogen here is in excess. How did I know that hydrogen is in excess? Because in the product, I ended up having unreacted hydrogen. So this is the excess hydrogen that did not do any reaction with the fluorine. So I knew that hydrogen is in excess. So if one of the reactants is in excess, the other one is going to be called the limiting reagent. And by definition, the limiting reagent is a reagent that is used all in order to form the product. So by knowing how much I used from the limiting reagent, I can relate that to the amount of the product that is produced. There are two cases to solve a limiting reactant problem. The first case is whenever I am working with 1 to 1 mole ratio of reactants. So we agreed that if we have two reactants, one of them is going to react completely to form the product. So it's going to react all to form the product. So it's going to be a limiting reagent. And the other one is going to be in excess. So one of those is going to be in excess, and the other one is going to be the limiting reagent. Um, the question over here is calculate the maximum amount of sulfur dioxide. So, what is sulfur dioxide? Sulfur dioxide is the product. So, I want to know how much a product. See, I want the amount of the sulfur dioxide that could be produced, that could be produced by reacting 55.2 grams of oxygen with 50.8 grams of H2S. So I am given the mass of each of the reactants. And I want to know how much am I going to get? What is the mass of the SO2 that I am going to get? Well, if I figure out which one of those is the limiting reagent, then I can use this information in order to relate it to the mass of the SO2 that is formed. So to start with this type of problem in here, and again, this type of problem is whenever you have a 1 to 1 mole ratio of reactants. Then you're going to go over these steps. So the first step is we're going to go ahead and since I'm given the mass, right, for each one of these reactants, I'm going to calculate the number of moles of each one of these reactants. So we're going to start by calculating the number of moles of H2S by knowing the mass and the molecular weight, of course. So this is 50 0.8 grams of H2S. The molecular weight of H2S is 34.1, so this is 1 mole of H2S. This is H2S divided by 34.1 grams of H2S, and I got the moles of the hydrogen sulfide. This is moles of H2S. Okay, so I calculated the moles of the H2S. I'm going to do the same thing and calculate the moles of the oxygen. So if I have 1 to 1 mole ratio, then I start by calculating the moles of each one of these reactants. Do the same thing. So 55.2 grams of oxygen multiplied by 1 mole of oxygen divided by 32 grams of oxygen, then I'm going to end up getting 1.73 moles of oxygen. Now I'm going to stop here and compare these two moles values together. And the one which is the smaller number of moles is the one which is considered to be the limiting reagent. So when I have a 1 to 1 mole ratio, I start by calculating the number of moles of each one of the reactants. And then the one which has the smallest number of mole, this is going to be the limiting reagent or the limiting reactant. We call it limiting reagent or limiting reactant. So you can easily see that H2S is considered is lower number of mole than the oxygen. So I would say that H2S is the limiting reactant. This means that oxygen is in excess because one of the reactants is going to be used all to get to the product and the other one is going to be in excess. So now I know that oxygen is in excess. The oxygen in excess is no use for me because I oxygen in excess will not give me any information about the product that is formed, which is the sulfur dioxide. What's going to give me more information about how much product I got is the limiting reagent because I know that I reacted all the limiting reagent, all of this to get to the product. So by knowing the amount of the H2S that I started with, I can relate it with the amount of the SO2 that I formed. So the rule says that get the limiting reagent, get the number of moles of the limiting reagent, which is the lowest number of moles. And then we're going to go ahead and get the mass of the product. So to get the mass of the product, I am going to start by, I know that I got the moles of H2S, right? Because H2S is what? Is my limiting reagent. So you start with the moles of the limiting reagent. We're going to change this. We're going to do a mole ratio. So we're going to change this into moles of the product, which is the SO2. So this is moles of the product in there. And then from the moles of the product, I can simply get the mass of the product. And this is what they meant by calculate the maximum amount. The maximum amount is the mass that that is formed of the product in there. So I need the mass of the product. To get the mass of the product, I need the moles of the product. And to get the moles of the product, I can simply relate it to the moles of the limiting reagent because I know that I used all of this in order to get the moles of the product. So I'm gonna start with how much did I use of the H2S? I used the 1.49 moles of the H2S. So this is 1.49 moles of H2S in there. I'm going to change this into moles of SO2. Look at the chemical equation, you guys. So I have 1 mole of H2S forms 1 mole of SO2, right? So I'm introducing the moles of SO2. So I would say 1 mole of SO2 is formed by reacting with 1 mole of H2S in there. So I introduce the moles of the SO2. Now I can change to the grams of SO2 by introducing the molecular weight of the product. This is going to be for every 1 mole of SO2. And this way I would go ahead and get the mass of the product that is formed. This is 95.5 grams of SO2, and this guy over here is the mass of the product. There's another name for it. We call it the theoretical mass of the product. The next case is whenever the mole ratios of the reactants are not the same. So we agreed that we have 2 reactants. One of the reactants is called a limiting reactant because we're using it all in order to get to the product, and the other one's going to be in excess. Okay, so here we have different mole ratios. So you look at your reactants, see the difference between the case and the case before. The case before we had a 1-to-1 mole ratio of the reactants. So we went with the number of moles of each of these reactants. We found out which one is the lowest. And we got that number of moles. We changed it into, we related it to the moles of the product, and then we changed it into the mass of the product. And we got the theoretical mass of the product. Here, to get the theoretical mass of the product, it's going to be a different story because the mole ratio of the reactants is not the same. So these are the steps that I want you to follow in this case. So we're gonna still get the number of moles of magnesium and the number of moles of oxygen. So get the number of moles of the reactants as usual. Okay, so that is we have the mass of the magnesium. You should be given the mass of each of the reactants. So we have the mass of the magnesium, which is given 2.43 grams of magnesium, and we're going to change this into moles of magnesium. So we're going to divide by the molecular weight. 1 mole of magnesium has a 24. Look at the periodic table, it's just an atom in there. So here you go. And I end up getting 0.10125 moles of magnesium. Okay, so you got the moles of magnesium for the first reactant. Now we're going to get the moles of the oxygen. This is the second reactant. So we are given, how much we are given? 3.20 grams of oxygen. So 3.20 grams of oxygen. We're going to multiply this by 1 mole of oxygen, and we're going to divide it by 32 grams of oxygen. And you're going to get the moles of the oxygen, which is 0.1 moles of the oxygen. Now here I cannot compare those two because already I'm starting with a different mole ratio. So I cannot compare those two and say, okay, the lowest one is the one which is the limiting. No, I cannot do this. There's an additional step. And what's the additional step in here? Because I have different mole ratios, I need to get the number of moles consumed of both of the magnesium and of the oxygen. Okay, so let's start with the number of moles of magnesium consumed. So the number of moles of magnesium consumed in there, because I want to get the moles of magnesium, right? So to get the moles of the magnesium, um, to get the moles of the magnesium in there, I'm going to go ahead and use the moles of the oxygen because I need to cancel the moles of the oxygen. So I'm going to say that, okay, I'm starting with 0.1 moles of oxygen in there, and I can relate the mole ratio that for every 1 mole of oxygen, I am reacting 2 moles of magnesium. So for every 1 mole of oxygen, I am reacting 2 moles of magnesium. And this way, I would go ahead and get the moles of the magnesium which is consumed. This is the moles of the magnesium that is used. So this is 0.2 moles of magnesium. Okay, so this is 0.2 moles of magnesium. I'm going to do the same thing for the oxygen. So for the moles of the oxygen consumed, I'm going to come over here and take the moles of the magnesium. So that is 0.10125 moles of magnesium. And I'm going to multiply that, check the mole ratio in the reaction. So for every 1 mole of oxygen, I am using 2 moles of magnesium in there. So the moles of magnesium and the moles of magnesium are going to cancel out. And I'm going to be left with 0.051 moles of oxygen in there. So now I want to figure out which reactant is a limiting reagent and which one is an excess. So what I look here is I start by looking at any one of them. So I'm just going to look at the oxygen in here. So the amount of oxygen consumed that I calculated is 0.05. I compare it with the moles of the oxygen. So this is oxygen, oxygen. So I compare it with the moles of the oxygen and say, okay, I used half what I have. Do you see that? Half what I have. So this means that oxygen is going to be in excess. Then definitely magnesium is going to be the limiting reagent. Let's check magnesium. So the amount of magnesium that is consumed, that is used, is zero point 0.2. Check what do I have in here. Do I have zero point 0.2? I don't even have the zero point 0.2. So it's more than what I have. So this means that the magnesium is going to be the limiting reagent. This means that I used it all in order to get to the product. So I can easily conclude that oxygen is going to be in excess and magnesium is going to be my limiting reagent. So now, since I figured out the limiting reagent, now I need to use the moles of the limiting reagent in order to get to the mass of the product. And the moles of the limiting reagent is not the ones that are consumed, you guys. The moles of the limiting reagent is the one that I already calculated from step number 1. So this is the magnesium in there. So it's going to be 0.10. Actually, let's go ahead and write what do we need to calculate. So I have the moles of the magnesium. I want to go from the moles of the magnesium to the moles of the product, which is the MgO, and then from the moles of the product to the mass of the product. Okay, so the moles of the magnesium is 0.10125 moles. I'm going to relate it to the moles of the MgO. So look at the equation, look at the chemical equation there. I have 2 moles of magnesium used for every 2 moles of MgO produced, right? So 2 moles of magnesium oxide is formed for every 2 moles of Mg that is used in there, and then I can relate this to the mass by using the molecular weight in there. So the molecular weight that is going to be mass of MgO, that is going to be 40 grams of MgO divided by 1 mole of MgO, and there for every 1 mole of MgO. So the moles of MgO and the moles of MgO are going to cancel out. Everything is going to cancel out in here in terms of units. Moles there cancel out, and then I'm going to end up having 4.03 grams of MgO produced. Okay, so whatever you are calculating, this is called the theoretical mass of the product. This is called the theoretical mass of the product. Let's have another example. Acetylene C2H2 burns according to the following reaction. So you can see over here, it's not 1-to-1 mole ratio. So this is similar to the above case. So suppose that 1.20 grams of C2H2 is mixed with that much oxygen. So same thing, I have the mass of of both reactants in there, different mole ratios. Um, what substances will be found in the mixture left when the burning is complete? So they are asking me here, which one of these reactants is in excess? So I need to find the limiting reagent and I need to find the excess. So we're going to do exactly the same thing. Find the moles of the C2H2. That is going to be 120 grams. It's the mass. Okay, and I'm going to go ahead and divide this by the molecular weight. This is C2H2 divided by the molecular weight, which is 26 grams of acetylene, and that is equal to that much moles of C2H2. Do the same thing for the oxygen. I'm starting with 3.50 grams. They are giving me 3.50 grams of oxygen, and I am going to divide it with the molecular weight of the oxygen. This is 36 grams of oxygen, and I'm going to get the moles of the oxygen. Now I'm going to go ahead and figure out the moles consumed as I did earlier for the acetylene and for the oxygen in there. So let's start with the acetylene. So to get the moles consumed of the acetylene, I'm going to use the moles of the oxygen. So that is equal to 0.10937 moles of oxygen. I'm going to relate this with the chemical equation in there. I know that for every 1 mole of acetylene, I am reacting it with 5 moles of oxygen, right? So for every 1 mole of C2H2, I am reacting it with 5 moles of oxygen, and that is equal to 0.021874 moles of C2H2. So you can easily compare. This is the moles consumed, and this is the moles of the acetylene that you calculated. So you consumed half of what you already have. Do you see that? So can say that acetylene is going to be in excess. So therefore, I can say that C2H2 is going to be in excess because I consumed half of whatever I calculated for acetylene. So this means that oxygen is going to be my limiting reagent. To double check that oxygen is my limiting reagent, I should get a number higher than this number whenever I'm calculating the number of moles of the oxygen consumed. So let's do that. Moles of oxygen consumed in there. So I am going to take the moles of the acetylene. Okay. That is going to be 0.046 moles of acetylene. Okay, and I know the mole ratio in here, which is 5 moles of oxygen for every 1 mole of acetylene, and that is equal to 0.23 moles of oxygen. So take a look over here. There is no way, because I have 0.1 moles of oxygen. I do not have 0.23. So there is no way. This means that oxygen is going to be the limiting reagent. So this means that oxygen is going to be the limiting reagent in this case. So as a summary, the acetylene is in excess and oxygen is going to be the limiting reagent. And this was the question. The question was, what substance will be found in the mixture left? So what is the excess? Which one is in excess? Oxygen. Well, no, I'm sorry, not oxygen. It is the acetylene, which is going to be in excess. So your answer is going to be acetylene. Acetylene. Another example, if 5 grams of carbon monoxide and 5 grams of oxygen are combined according to this reaction, which is the limiting reagent. Okay. Again, you look here, similar to the steps earlier, you don't have a 1-to-1 mole ratio, you guys. So if there's no 1-to-1 mole ratio, we're going to follow the exact steps in there. We're going to calculate the number of moles of carbon monoxide, which is 5 grams of carbon monoxide multiplied by 1 mole of carbon monoxide divided, this is the molecular weight of carbon monoxide, and we will get the number of moles of CO. We're going to do the same thing for the oxygen. So we're starting with 5 grams of oxygen. This is 1 mole of oxygen divided by 32 grams of oxygen. This is the molecular weight of oxygen. And then we're going to go ahead and calculate the moles of oxygen consumed and the moles of carbon monoxide consumed. So to calculate the moles of CO consumed, we're going to use the moles of the oxygen. So that is equal to 0.1562 moles of oxygen times, just go ahead and do a relationship in there. For every 2 moles of CO, I am reacting it with 1 mole of oxygen. So this is 2 moles of CO, 1 mole of oxygen, and I can get I will get 0.3124 in there. Okay, that is the CO. Notice over here, you compare the moles of the CO consumed with the moles of the CO that you calculated earlier, and you can see the number is higher. I don't have this amount. So I would say that definitely the CO in this case over here is going to be my limiting reagent. So this one is going to be my limiting reagent. This is more than what we originally have. So this makes the oxygen in excess. So let's go ahead and check here for the oxygen. We're going to use the moles of the CO. It's 0.1785 moles. And I'm going to relate it to the mole ratio of the oxygen to the CO in there, and that is 0.08925 moles of oxygen. So now I'm going to compare the moles of the oxygen with the moles of the oxygen in there, and you can easily see that this is more than this. So I did not use it all, right? So oxygen here is going to be in excess. So therefore oxygen is in excess. So when you find the theoretical yield, and you already have the actual yield, you can calculate the percent yield of the reaction. So the theoretical yield is the mass that we already were finding in the product. So for example, here in this example here, whatever mass we got in this example, that was the theoretical yield. So any mass that you get in the product for the product, that is called the theoretical mass or the theoretical yield. So by knowing the actual yield, you divide it by the theoretical yield, you multiply by 100 and you get the percent yield. Let's have an example on this one. So, okay, so tests are to be conducted on a new anti-cancer drug, and you are to prepare a fresh supply for human subject studies. You discover that you were able to prepare that much of the substance, although it was theoretically possible. So this is the experimental, and this is the theoretical. This is the actual, and this is the theoretical in there. So you simply divide those over each other. It's the mass, it's the actual mass. So it has to be both in grams, okay? Divided by 1.433 grams, and you have to multiply by 100. Multiplying by 100 is a must because it's a percent yield, and that one is the 93.86%. Another example, you are given a theoretical yield of 73.7 grams of SO2 was done in the lab, and only that much was collected. So this is the experimental part. This is the experimental mass, or the experimental, which is the actual mass in there. So this one is the actual, since we're using the word actual. And this one over here is going to be the theoretical. Okay, this one is going to be the theoretical yield or the theoretical mass. So the percent yield is equal to the experimental divided by the theoretical times 100. So it's equal to 42.7 grams of SO2 divided by 73.7 grams of SO2 times 100, you guys, and that is equal to 57.9%. Notice that the yield cannot cross 100 because it's a percentage, so pay attention to that. And always the higher the yield, the higher the percentage of the product that you form. This is the end of the chapter. Please practice your homework, and the key for the homework is on eCampus.